Alternating series. So what is this? This is a series whose terms alternate. What do they alternate? They alternate from positive to negative. From one term to the next. Okay. When you see this -1 to the n, this is an alternator. I call it my sign changer. As n goes between even and odd, the power makes the n power makes the -1 go from an odd number, which makes a negative number, to an even number, which makes a positive number. Okay? So an example, something that's alternating, like 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, and so on, ... Okay? We're alternating between positive and negative each time. So plus minus, plus minus, plus minus, and so on. An example that is not. So could we write this in a series? Yeah, I think we could. N equal 1 to infinity. Well, what does this look like? If I made all these positive, that would look like the harmonic series, right? So I know it looks like this, but what's going on here? I've got a sign changer, so I've got a -1 to the n, but if I put it to n and I plug a 1 in, that first term, n equal 1, gives me 1 over 1 times -1 to the 1, which is -1. We don't get -1 for the first term, so I either need to subtract 1 or add 1. Okay, so whatever works for you, just you need to change that. And so if it's -1, then you get that to the 0, which gets you a +1, and now we're good to go. Okay, so this series is equal to that right there. Okay, now let me give you an example of one that's like not an alternating. So not alternating. Okay, so don't get confused here. If I had like 1 minus 1/2, okay, plus 1/4, plus 1/8, plus 1/16, minus 32, and so on. This is a negative here, but then it's positive, 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 negative again, okay? This isn't alternating. This is plus, minus, plus, 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 minus. Okay? The only way that it's going to be alternating is it swaps between plus, minus, plus, minus, plus, minus. Okay, so if that was negative, then we'd be good to go, but it's not. So this does not work. All right. Now, for the alternating series test, now that we know what an alternating series is, let's do the test. So the alternating series test for convergence of infinite series, I want an to be positive. Now you might be saying, well, Mr. Clark, didn't you just say that it's alternating between negative and positive? Well, yeah, technically, but the an part is this part right here. This would be my an part here, okay? And so then we have our sign switcher over to the side, all right? So that's what I'm talking about when I'm talking about my an. So what am I saying here? I'm taking the limit. So okay, let me rewrite that. So because what happens is if I start taking the limits of this thing, that's going to get pretty nasty. So I don't want to look at my sign switcher. I only want to look at, my AN part. So if the limit as n goes to infinity of a sub n goes to 0, okay? So we got to have this to be true. And what else needs to be true? AN is greater than or equal to AN plus 1 for all n. Okay? So what does this mean? This means we're decreasing. Okay? Each term after is a little bit smaller. So each term decreases in size, and terms are going where? Are heading to 0. Okay? So the terms are heading to 0 and the terms are decreasing. So if this is true, then by the alternating series test, the series n equal 1 to infinity of my sign switcher and my AN converges. See how we separated out the AN from the sign switcher there? So that's why we can look at just the positive ANs there. Okay? So all I have to do is I have to show that the series is going as the sequence is limiting to 0, and that the sequence is not decreasing but non-increasing. Okay, so we talked about the nuance between the difference of decreasing versus non-increasing. Decreasing would be like strictly greater than. Okay, that's decreasing. Non-increasing would be greater than or equal to. All right, so the sequence AN is heading to 0, and it's non-increasing. If it's non-increasing and heading to 0, then the alternating series converges. All right? Now, give you an example. Series n equal 1 to infinity, negative 1 to the n plus 1 times 1 over n. Okay, we just worked through this problem just a second ago. Okay? Right here. All right? So let's see if we can solve it. So to use the alternating series test, AN needs to be positive. AN is defined to be 1 over n. By golly, this is greater than 0. For n greater than or equal to 1, we start at n equal to 1, so we're good to go. Okay. I know that those are 1 is greater than 0, and so the reciprocal is definitely greater than 0, so we're good there. Okay. I need to check the limit as n goes to infinity of a sub n, which is equal to the limit as n goes to infinity of 1 over n, which equals 0. Check. We're good to go here. Now I need to show, so I've got my scratch work over here. Okay? I want to show what? I want to show AN is greater than or equal to AN plus 1, right? So what's that mean? 1 over n is greater than or equal to 1 over n plus 1. That's what I want to show. Now I know both of those are positive, okay? If I do the reciprocals of each, they flip around, and so I get n plus 1 greater than or equal to n greater than 0, okay? Looks like this is a true statement, because if I subtract n here, then 1 is greater than or equal to 0. I think that's a true statement. All right, so let's build up from there. Okay, so let's just work backwards. So I'm going to start with the ending. Start with something we know to be true. That's easy to say. If I go back this way, the opposite of subtracting in is adding in. So if I add in to both sides, I get n greater than or equal to n plus 1. Now, what do we know about n? We know from our assumption that n is greater than or equal to 0. Or greater than or equal to 1, rather. Okay. So I just added n to both sides here, right? And so now that I have this to be the case, then the reciprocal, okay, so this tells me what? So 0 is less than 1, less than or equal to n, less than or equal to n plus 1, okay? The reciprocal tells me what? Tells me that 0 is less than, well, what's the biggest one? N plus 1, so then the reciprocal is this. And then 1 over n, and then 1 over 1, right, which is just 1. So now I have a sub n less than or equal to a sub n plus 1 for n greater than or equal to 1. Okay, that was our assumption right there, right? So this is what I want to show. So basically, the idea here is start with what you want, work down until you get something you know is true, and then just reverse the steps back. So start with what you know is true and get to what you want, okay? Sometimes it's easier when you're working a difficult problem to start at the answer and then work backwards, okay? So now that we've got number 1 and number 2 satisfied, then what do we know? By the alternating series test, so therefore, by the alternating series test, now I will let you abbreviate AST if you want. By the alternating series test, the series n equal 1 to infinity of negative 1 to the n plus 1, 1 over n, converges. Okay. All right. Not too bad. Let's try another one. Example. Series n equal 1 to infinity. The sine of parentheses n 2n minus 1 pi over 2. And then square root n squared plus n, obviously n squared plus 1, all square rooted, divided by 2n. Oh my goodness, we've got sines and square roots. Oh my gosh, this is going to be hard. Well, guess what? This right here, this is a sneaky sign changer. All right, sneaky. If you don't know what's going on, just start plugging in values. The first one's n equal to 1. So that's sine of, if I plug a 1 in there, what's that going to get me? That gets me 2 minus 1, that's 1, pi over 2. That's 1. If I plugged an n equal to 2 in, that's sine of, well, I plug a 2 in, I get 2 times 2 is 4, minus 1 is 3, pi over 2. Okay, unit circle, if you think about a unit circle, that's pi over 2, so that's 1. But 3 pi over 2 is 1, 2, 3. That's negative 1. Okay? And then this is going to produce 5 pi over 2, which would go back to 1. So what's happening here? This is a fancy way to say negative 1 to the n, and you can do plus or minus 1. I'm just going to do plus 1 here. okay? So these are the same thing, all right? It's just a sneaky way that you might see some problems do things. So be careful. You got to be careful for those sneaky mathematicians. All right. So really, our a sub n is the square root of n squared plus 1 over 2n. Okay? Over 2n. Now, what I want to do is I want to make sure that this thing is positive. Okay? So for n greater than or equal to 1, what do I know? N squared plus 1, that's definitely greater than or equal to 0, right? That's greater than or equal to 0. Now, if 2n is greater than or equal to 2, that's greater than 0. So square root is still greater than 0, right? So something that's positive divided by something that's positive, that's definitely positive. All right, so kind of some hand waving there, but a sub n is definitely going to be positive. We can actually drop the equal to because n here is greater than or equal to 1. So I know for a fact that this thing right here has got to be bigger than 0. Okay? The smallest the numerator can be square root of 1. Okay? So we are good to go. All right, this is positive. Smallest that's going to be, well, if it limits out, it's going closer, closer, closer. It's asymptotically approaching 0, but it doesn't get there, right? Okay, so we're good. an is positive. Now what I want to do is I want to take the limit as n goes to infinity of the square root of n squared plus 1 over 2n. All right, this could be a little challenging, okay? Now, intuitively, you might know what's going on here. In here, the squared, n squared is the dominant term. So really the 1 doesn't contribute too much at infinity. But say, you know, it's basically like square root of n squared, which is basically like n when we're going positive direction. So this is basically some hand waving n over 2n, which limits to probably 1 over 2, right? But let's do some math to back that up, okay? So let's do some math. So what I can do in the numerator is I can factor out an n squared from both terms. Okay, so I'm going to pull an n squared out of both. I have 1 plus and then 1 over n squared. All right, that's a pretty good factoring trick. Helps you because since we're talking about n going to infinity, what's inside the radical is positive, so you can actually break that up into two pieces. That's really going to be helpful for us because now you're going to have square root n squared and square root 1 plus 1 over n squared. And your limit as n goes to infinity of this 2n. This thing reduces. Okay, this reduces to n, or absolute value of n, over 2n. And we can drop the absolute values because we're heading to positive infinity. So it behaves the same way. And so what's happening here? These cancel, and I get what? I get square root of 1 plus 0. This piece here goes to 0 over 2. So this is 1 over 2, just like we hypothesized, right? So this limits to 2. Yikes. Yikes. That an just limited to 2. What does our test say? We need to do what? We need to limit to 0. So the alternating series test just failed here, didn't it? It just failed. Okay? However, if I have a limit as n goes to infinity of an and it equals 1/2, okay? This is not equal to 0. Therefore, what? By the nth term divergence test, okay, by the nth term divergence test, the series n equal 1 to infinity of sine 2n minus 1 pi over 2 times square root n squared plus 1 over 2n diverges. Okay? Diverges by the divergence test. Snuck up on them, right? Okay. So, let's try another. Series n equal 2 to infinity, negative 1 to the, and then 1 over ln n. Okay. Now, this is really kind of an interesting idea, right? I mean, when we looked at just the harmonic by itself without the sign changer, we decided this is 1 over n, 1 to infinity diverged, right? However, when you've got the sign changer, now all of a sudden that something that would diverge is actually converging, okay? So these pluses and minuses actually make a difference, don't they? So this one right here, negative 1, and then we'll do to the n. This sign changer gives me hope that this 1 over natural log of n converges. Now, typically, if I would have just had 1 over ln n, this would definitely diverge. I mean, that's growing slower than 1 over n. And if 1 over n diverges, or it's shrinking slower than 1 over n. And if 1 over n diverges, then for sure 1 over ln n diverges. But this negative 1 to the n power is kind of our game changer. So for sure, let's make sure an is greater than 0. Now, if an is 1 over ln n, that's an, okay? And I know n is greater than or equal to 2, that's what we're told here. So what does that mean? So I want to show that ln n is greater than 0. Okay, ln n is greater than 0. All right, how do I do that? Well, I probably need an ln n somewhere, so I'm going to ln both sides. Okay, greater than or equal to ln 2. Now, ln 2 is a positive number, so that's greater than 0. And then, what do I have? 1 over ln 2 is greater than or equal to 1 over ln, which is greater than 0. So, voila, it's done, we're okay. All right, so let's see here. I need to show the limit as n goes to infinity of an is going to 0. So this is a limit as n goes to infinity of 1 over ln n, which is equal to 1 over, looks like infinity, which is going to be 0. Bingo. All right, we're good here. Number 2, I need to show, so what do I want? I want an to be decreasing. So an is going to get smaller and smaller as I go out. So what do I want? I want 1 over ln n to be greater than or equal to 1 over ln n plus 1. So how do I do that? Let's just start with what we know, okay? So I know that these terms are all greater than 0. Okay, I already showed that here. So every an term is bigger than 0 for n greater than or equal to 2. So what does that mean? The reciprocal, ln n plus 1, is greater than or equal to ln n, which is greater than 0. And then if I everything, because e is continuous function, then I've got n plus 1 greater than or equal to n, which is greater than 0, obviously. Okay. And, this is truly, we have it set n to be greater than or equal to 2, so I could make this an even stronger case. Okay, I know that there. So, I think I'm okay now. All right. think it's okay to say this. This is a good place to start. So 2 less than or equal to n is less than or equal to n plus 1. And then what's the next line say to do? It says that 0 is, well, actually, yeah, I mean, I guess I could do this. N and then less than or equal to n plus 1. So what does that mean? That means 0. And then you have the reciprocal, ln n plus 1 less than or equal to 1 over ln n. Okay. Wait a second. What have I done here? I did something too fast. Okay, let me go back. So this needs to be, I need to natural log things. ln n less than or equal to ln n plus 1. All right, now I'm okay. So then I can do the reciprocal, okay? And so when I do this, 0 less than 1 over ln n plus 1 less than or equal to 1 over ln n. And this is what I want. an plus 1 less than or equal to an. Okay? This is what I'm looking for right here. So this and this. Therefore, so you see how we just went line by line by line, the opposite of what my scratch work was, right? Okay, so instead of doing an e to both sides, a ln, okay, it's the opposite function. All right, so therefore what? Therefore, by the alternating series test, the series n equal 2 to infinity of negative 1 to the n, 1 over ln n converges. Okay, this series converges. All right, guys, in the next video, we're going to talk about alternating series and the remainder.